Hello, everyone, and welcome to this new episode of the E-SWAN Sustainability Working Group webinar series. I am Sophie Schabanski from the Royal Belgian Institute for Space Aeronomy, and I will be your host today. Today, we have the pleasure of welcoming Jan-Steffen Fischer, who will present the results of his research on the environmental impact of the space transport system. Jan has a Master of Science degree in Aerospace Engineering from the University of Stuttgart and is a PhD candidate and research associate since 2021. All the E-SWAN Sustainability Working Group's webinars are recorded and replay is available either on the E-SWAN website or on the YouTube E-SWAN playlist. There is a Q&A tab where you can type in your questions at any time, and Jan will address your questions at the end of the talk. So, Jan, the floor is yours.
Yeah, thank you very much for the introduction and for the opportunity to talk today. I will present now some results of the research that we've conducted here at the university since now 4.5 years. And first of all, I would like to talk about the motivation why we should look at the environmental impact of space transportation systems. What we see here is the history of space launches, so the total number of successful launches shown in green and the unsuccessful in red. And what we see here since the beginning of the 2020s is a significant raise with about 22% per year of those launches. This is expected also to continue in the next few years with about 15% per year. So we are now reaching here from about 100 launches per year, an average, to maybe in the future thousands of launches per year. On the same side, we have here the planetary boundaries that needs to be considered, of course, because we are currently changing as humanity the planet and also our environmental systems around in a way that we leave the planetary boundaries that enabled us to develop as humanity. So therefore, it makes also sense to look now at the impact of space launches to not have a significant impact in the future that we maybe could avoid by acting now. So today I'm gonna split my talk into those 5 life cycle phases of launch system. First of all, I'm gonna talk about the research and development phase. Afterwards, about the production of the launcher, the launch phase and the reuse phase, and then the demise at the end. So now let's start with the research and development phase. And here it is quite interesting. If we look in the history of spaceflight, we saw in the past that the technical drivers for the development was that we need to achieve a specific point as fast as we can. For example, first man in space, first man on the moon, and so on. And then spaceflight diverted more to a commercial-driven technology, which it is now, mainly, for example, driven by the new developments from SpaceX with significant lower launch or payload costs. And then in the future, hopefully, we might also establish a new dimension of technical development, sustainability. And how is this achieved? For this, we have life cycle assessment. This is written down into ISO standards, and it is divided in 4 stages. First of all, the goal and scope definition. So I define what is the focus of my life cycle assessment. In the next step, the life cycle inventory analysis, where I basically do a digital twin of my production. So I count every material that I need, every energy what that I need, and so on and so on. And with that, in the end, I'm doing my impact assessment by then characterizing every flow that goes out to the environment. And in the end, of course, I'm going to interpret my results. This is specifically also written down for space systems in the ESA lifecycle assessment guidelines. Now, since last year, there's an updated version. And ESA has also its own database with 19 environmental indicators. And additionally, the European Commission is currently developing the PEFCR for space guidelines. There was a draft published last year, and it is intended to be in law by 2030. Here I have a small overview of the different environmental indicators. I will not go into detail of every now, but I want to highlight some, which is the global warming potential, so the climate impact, the ozone depletion potential. Then we have different factors looking at the impact on the air, on human health, then resource depletion, energy consumption, eutrophication, ecotoxicity, and so on. Now, when we have developed the launcher, we will now produce the launch system. And here we did a study together with a European launcher manufacturer, the Ariane Group. They gave us data on the environmental impact of each subsystem, and then we compared different stage architectures and propellant systems with each other. So here we have an example of LOX kerosene engines, so like, for example, the Falcon 9 system. And we have here shown for different environmental indicators the impact. Blue represents the production of the dry mass, and green represents the production of the propellants, divided by the core stage and the upper stage. And what we can see here for most of the environmental indicators, we see that the impact of the production of the dry mass is significantly, except here the water depletion and land use. But for most of the environmental impacts, the dry mass production is the main driver here, and the propellant production only is about 30%, something like that, in that order of magnitude. This significantly changes if we look to another launch system, which we have here. This is a launch system which is basically an LOX hydrogen system in the core and upper stage and the solid booster, so a system like the Ariane 6. And what we see here is the big share of the green parts, by meaning that this is the propellant production, which has an impact of more than 50% for nearly all of the environmental indicators. And the phase of the dry mass production is here significantly lower. So what I want to show with that, it is really difficult to set this up for a general quote, but we need to look in detail at the specific launch system and the propellants that are used for each launch system if we want to calculate the impact of the production phase. We compared this now to the world population. So for the environmental indicators that I've shown, there are some data for the population of 6.9 billion people worldwide, which represents the annual environmental impact of those world population. And with this, we can now normalize our production of a launch system, which is done here, for example, for a launch system with hydrogen core and upper stage and solid boosters and 25 tons payload capacity to the low of orbit. And we can see here that we do have significant impacts, by meaning that we have more than 10,000 people equivalent for the freshwater eutrophication and the freshwater toxicity, and also a quite significant impact, for example, for the global warming potential, the resource depletion, and then also acidification and water depletion. So now maybe one may ask if it is a positive impact if I reuse my system for multiple times. And this was also done in our study here, where we took this data and looked at different ways to recover a stage. So for Falcon 9, this is done normally in two ways. There's a drone ship landing. So here, downrange of the launch site, the core stage comes back into the Earth atmosphere. There's a deceleration maneuver and then lands in the ocean on a drone ship. The other way how it is done today is return to launch site, by meaning that the core stage is then flying back near to the launch site and landing there on the land. Both of them will reduce the amount of payload that can be taken into orbit, because you need to have some propellant in your stage to land. In the case of the drone ship landing is about 20%, and in the return to launch site, it is about 40% of the payload mass reduction. Now we compared this data with an expendable system. So we took here the assumption that we use the core stage only once, and then shown here in red is the drone ship landing, and in green is shown the return to launch site landing. And those numbers here are calculated per kilogram of payload that is brought into orbit. Now I have here 3 different environmental indicators as an example. First, I will talk about the climate impact. Here is shown the climate impact over the number of uses of the launch system. So what we can see here is a positive effect of the drone ship landing operation after 2 reuses. And if we look at the return to launch site, we see a positive impact after 10 reuses. So for the resource consumption, this is significantly better, because after 2 or 3 reuses, I already have a positive effect. Makes sense, because I don't have to reproduce my core stage. And for the water consumption, we don't see a positive impact. This is due to the high impact of the propellant production, which is here more than 80% driven by the propellant, and therefore we don't have here positive impact for water consumption and land use potential. In this study, we didn't consider the launch missions. I would like to talk about them now. So the first approach when we're talking about launch mission is, of course, calculating then in a stoichiometric approach for the Falcon 9 core stage, which is driven by LOX and kerosene. We only get, in a stoichiometric case, water and CO2. And for the Ariane 6, which uses the LOX and hydrogen system, the core stage only produces water in an ideal case, but then we have the solid booster, which produces carbon dioxide, nitrogen, aluminum, and chlorine. And we compare that here in a simple way with a normal commercial aviation flight, New York to Singapore, which is the longest commercial flight available, which is proceeded, I think, 200 times per year, something like that in the order of magnitude. And we see here, if we compare the CO2 with the Falcon 9, that we have here nearly the same order of magnitude of CO2 emitted by 1 commercial flight, and here by 1 launch. So if we only look at the CO2, it seems not to be very significant. But as you may know, in aviation, CO2 is only about 1/3 of the effects, and 2/3 come from other effects here. And it is the same, of course, for launch systems. And additionally, of course, launch systems do not run in a stoichiometric consumption in the engines. And therefore, we developed our launch mission tool, which is also available open source. So if you're interested about this tool, you can find it on GitHub available, and we are also currently preparing a publication for that. So the tool calculates first the trajectory of the launcher. And if we have this, we get also a mass profile, by meaning that we know in which altitude and which position the propellant was burned. But to know this, we need to know where the gravity turn happens. So if a launcher accelerates, at some point it will then do a small deviation in its flight path angle, and then slowly convert to a horizontal flight to build up the necessary velocity to go into an orbit around Earth. So this is, for most of the launch systems, not very known, and also the thrust reduction that happens during the ascent, because the launcher wants to avoid a high aerodynamic pressure when it goes through the Mach 1 area. And also, this is a simplified approach, of course, that we're using here, because we're using here some basic drag estimations. So if we now look at the trajectory, we compared the data that was calculated with the tool with the available video stream trajectory, and we see that it is more or less a good fit. So we use it as a emission calculation for or emission estimation for the launches, and we can see here the distribution of the propellant burned in the atmosphere. So what we can see here is, of course, an exponential reduce of the propellant consumption with a specific lower consumption here in the altitude bin of 5 to 10 kilometers. This is due to the thrust reduction that happens here to avoid high aerodynamic forces. Then we have nearly no emissions here in the range of 65 to 75 kilometers. This is due to the stage separation that happens here. And then again, above 75 kilometers, we do have emissions from the upper stage, which is then burning there. In the next step, if we want to calculate the launch emissions, we using here NASA CA or Cantera, which uses the propellant type, temperature, the mixture ratio, nozzle ratio, combustion pressure, and engine cycle to calculate the emissions. So we get now at the engine exhaust level the species. What we don't know exactly where the freezing of the reaction occur, because we here in the nozzle the plume is expanded, and therefore at some point there's not enough interaction between the species in the nozzle, and so there's a freezing point. But we can estimate it by calculating it in the equilibrium and it throws from the nozzle throat on way. And with NASCA, we only have a one-dimensional calculation approach. So this is normally in engines we have an inhomogeneous mixing. So here we also have a limitation in our calculation. But what we can see here, if we calculate here, for example, the Merlin 1D engine, that we have significant amounts of carbon monoxide, carbon hydroxide, hydrogen, and water, but also some minor species, for example, like hydrocarbon oxide or others. It depends a bit if we consider a gas generator or not. A gas generator normally has an additional exhaust plume on the side, and gas generators are normally running under very high fuel-rich conditions. So that means that, for example, a lot of black carbon or soot comes out of the gas generator. So this is also considered here. Now, in the next step, if we want to model those emissions, we use here an assumption of a control volume. And in this control volume, on the one side, the hot gas from the nozzle exit goes in, on the other side, surrounding air, which is here calculated with this NRMSys model. So it is specific to time, altitude, and location. And as an output, we get then the final emission index per species. But currently, we do not really know how much air interacts with the hot rocket plume. So therefore, we established here an uncertainty factor, which I will show later on the results then, depending on this. And the NOx formation is therefore also very dependent on this factor. And the black carbon formation, unfortunately, if we use this methodology, the CEA approach assumes that every black carbon that goes into this control volume is burned in the atmosphere. So we use here an additional methodology published by James et al. Because it is known from measurements that there is definitely some black carbon at the end, but it's not very uncertain how much it is. And also the tool doesn't give out the particle size distribution. And I will talk later about why this is important. So we calculated the launches from 2019 to 2025 based on the launch data, which was published from McDowell. The launcher data was taken from literature for most of the launches. Of course, we do have some launches, for example, the North Korean launchers or the Iranian launchers, where we don't have enough data. There we use the stage optimization approach to calculate this. And for those launchers who launched more than 10 times, we also looked at engine-specific data so that we know the exact mixture ratio, the combustion pressure, and nozzle expansion ratio that have an influence on the nozzle exit exhaust. For most of the launchers, therefore, we use general data for our engines. And here are some facts about the last few or the last 7 years. In 2019, we had 102 launches. In 2025, it was already 329 launches, so a growth of about 330%. And if we have a look who launched the systems, that's also quite interesting because more than half was launched by SpaceX. China had about 1/3 of the launches, and the remaining launches were then done by Russia, New Zealand, which is the Electron launcher, and Europe itself only had 8 launches 2025. If you now have a look on the emissions, we calculated all the launches and plotted them here with the uncertainty that is driven by the uncertainty factor, so the mixture between the surrounding air and the exhaust. We can see here the uncertainty area that we get for our results, and shown here in green is the frozen approach. So by meaning that we assume that the chemical reaction freeze from the nozzle thread on. In blue, which is mainly overlapped by the green area, we show here the equilibrium approach, and here in orange is shown the literature approach, which is based on altitude-dependent emission factors, so not engine-specific, but altitude-dependent emission factors. And what we see here in literature that the amount of CO2 is overestimated while the amount of carbon monoxide is underestimated. With our approach, we land here in the same order of magnitude for both of the species with a very high uncertainty range for the carbon monoxide, because this is mainly driven by the amount of afterburning. We have here on the other side shown the water and the hydrogen emissions. So for water, this is a very small area of uncertainty, so we do quite well understand how much water is emitted. But for hydrogen, this still is a significant area of uncertainty. We also calculated this, for example, for chlorine species, which have a significant impact on ozone. And here we see different chlorine species, so chlorine as an atomic and a molecular way, and then chlorine in combination with a hydrogen molecule. And we see here that we have more chlorine in a molecular way, and also more nitrogen or nitrous oxide, which is shown here on the right side, with emission indices. But we also see a significant OH emission, which is not covered by literature yet. So maybe this could also be significant for further calculations regarding the climate impact from that. Now, this is a very rough estimation of the total CO2 equivalents. The numbers that are shown here are derived by tropospheric factors, which were published from IPCC and Lee et al. And applied to the complete atmosphere. So these are very, very uncertain, and this is just to give an idea of an order of magnitude in which emissions do have a significant impact of the climate impact according to the knowledge in the troposphere. And with that, we see that if we compare the total mass of emissions, we see that there was a growth of about 450%, so more than a growth of the number of launches, because, for example, the Starship has already, with one launch, the impact of 10 launches regarding the emissions. We see here a significant growth of the launch emissions in total, and if we compared it to the emission of aviation in 1 year, in 2019, we see that it is not really significant. It's in the order of 0.05%. But if you compare the impact, we see that the space launch emissions do have an order of magnitude higher impact than the emissions if we compare them with the aviation each time. So therefore, we might get with already a significant number of launches in the order of 10,000 launches or something like that, in the same order of impacts if we compare it to aviation. So therefore, this is a motivation to do further research on, because the numbers that we have here are, as mentioned, not valid for the higher and upper atmosphere, and I will talk later about the impacts there. So this is a motivation why we need to look in detail more on that. Now, if we have launched our system to space, at some time it will come back to Earth. And for this, we also published a re-entry emission tool, which is also available on GitHub here. And with that, it is an estimation of the emissions that are currently there. So we use here drama as a trajectory calculation, which takes a generic model of an upper stage here into account with different subsystems and different materials, which are then adapted to the geometry and mass of each upper stage. Then we have varying entry conditions by meaning the velocity, angle, location, and time where it comes into Earth. Then Earth's atmosphere, and then as an output we get again here the flight path and the mass distribution again over altitude. The problem with drama is that it has a specific fragmentation point, and this needs to be estimated. And also drama has a very broad approach on calculating fragment size, so there may be better tools, but drama is available open source. And also the heating in drama might be underestimated because it is a ground risk assessment tool originally. So it has a conservative approach regarding the heating and therefore the mass loss in the atmosphere. And drama is also a stochastic calculation, so there are still, of course, some uncertainties where exactly the stage will come down. Once we've done the trajectory calculation, the emission calculation is here done in a two-step approach. In the first step, we estimate the heated air again here with an equilibrium solver, which is, of course, a very big limitation, because normally in the upper atmosphere, you will not get an equilibrium chemistry, but at least it gives us an order of magnitude of the emissions that occur and an idea which species occur in which layer of the atmosphere, to be then refined, of course, in the future if we have better measurement data available and better models available. In the next step, here the material emissions are calculated assuming a constant temperature and pressure. And with that, we can then calculate the emission in each altitude. And again, we have here the uncertainty how much air interacts really with our material and the shock wave. And therefore, we also use here again an uncertainty factor. And as mentioned, is an equilibrium calculation. And again, we do not have any information about the particle size from that. So if we now run this calculation, this is shown here for an example re-entry. We see here a significant dependence on this uncertainty factor regarding the nitrous oxide production and the amount of aluminum and aluminum oxide that comes out of it. So this is really still big uncertainty. Again, here we build up a database of the rocket body re-entries from 2019 to 2025 based on the catalog by McDowell and the space track data available. The stage data was then here again taken from literature and the Jonathan's catalog of space objects. And we used then generic models to adapt them by mass, diameter, and length, and then calculated here the re-entry for each of those upper stages. And for the Ariane 6 launcher, we got quite good data from Ariane Group about the mass share and the materials. So this was used and adapted to the other systems. And what we can see from that is that if we compare here the total aluminum that is put into the atmosphere, which is shown here in orange, to the final emissions, which are shown here in blue, calculated with the CA approach, we see that we have at the beginning only more or less only aluminum emissions, and then the lower we get higher amounts of aluminum oxide, which is of course clear because we have more oxygen that can react. But we also see that most of the emissions occur in the mesosphere here. And then if we look at the nitrous oxide that comes from the heating of the air, we see that this is more here in the stratosphere area. And this is quite interesting, I think, because it shows really different emissions in different altitudes or layers of the atmosphere. In total, we had about 1,400 tons of emissions in the last 7 years, which seems not to be very much, but I will go into detail on one type of that emission in a second. Compared to launch emissions, also this is in a 0 point order of magnitude compared to the launch emissions. But what is really the problem at the moment, we have a lot of different species because we have a lot of different materials, and still there are no public available catalogs on all the available materials that are used for upper stages. So we don't have yet a complete overview over the potential species that could be produced in the atmosphere. And also, maybe one of those species might have a significant impact already in parts per billion or trillion concentration. So this is really a research gap where now a lot of research projects coming up and focusing on the potential impacts from that. As mentioned, the total amount of emissions seems not to be very high, but if we compare this to natural resources of emissions into the atmosphere, which is mainly the impact from meteorites, we see that, for example, for the aluminum, we are already in the order of magnitude of the aluminum emissions into Earth's atmosphere. And as we see or expect a continuous growth also in the future, this might get more and more relevant, so that we are actively changing here the composition of the atmosphere. And this was also measured, as you may already know, by Murphy et al. In 2023. They flew with this WB57 in the area of 12 to 20 kilometers and the sampling of the sulfuric acid particles, and 10% of them are from re-entries or rocket launches so far. And this was only in 2023, where we just started all the space activities that I mentioned. So now I talked a lot of those emissions, and for the launch emissions, I already talked a bit about the climate impacts, but I would like to highlight them now a bit more in detail. Regarding the climate impact, there are a few impacts that we have to look at. Rocket launches are the only human-made objects that fly through the complete atmosphere, and also, of course, they're re-entering space objects then. Because the aviation, everything normally influences the climate happens here in the troposphere and lower stratosphere. And for rocket launches, we do have the uncertainty of the impact of the cloud formation, which happens in the mesosphere and stratosphere. It is estimated that rocket launches may lead to more polar stratospheric and mesospheric clouds, but it is not sure yet what is the impact from that. The CO2 emissions are a known greenhouse gas, but as we've seen, for at least for the troposphere, this is not in a relevant order of magnitude. But still, it is, to my knowledge, not really clear what happens here in the upper atmospheric layers. Soot is currently the most discussed rocket launch emission because it is assumed that the soot particles are in a micrometer range of particle size. And they can stay here in the stratosphere for several years, and also in the mesosphere, due to the mesospheric winds happening, they will then be washed towards the poles, so that they stay there for a few years. And it's currently in different climate impact studies. It is uncertain what is exactly the impact of those soot particles. It is estimated that it might be in the order of a factor of 1,000 compared to CO2, but still uncertain that it might heat, for example, the stratosphere, which I think all the studies show currently, and therefore also accelerate, for example, ozone depletion. And the same is for aluminum, because we don't really know what is the impact here. There were also some proposals for geoengineering to launch a significant amount of aluminum particles in the stratosphere, with yet unknown impact on the radiative forcing. And there might be also coming from reentries more unknown species with potential significantly high impacts. But in total, globally, the impact is estimated to be lower than 1% at the moment. Now we do have a second impact, which was or where we had more research in the past, and there's now research again, which is the ozone impact. As you maybe know, the ozone hole is now getting smaller and smaller in the past few years. But there are also concerns that the rocket launches might lead to more ozone depletion, and then might have a negative effect here. And there are different chemical processes occurring. So we have the nitrous oxide, which are, of course, part of the natural stable balance of ozone depletion and ozone formation. But of course, if we put here significant amounts of nitrous oxide into the atmosphere, we also have an impact on this natural balance. Chlorine species have the known effect as carbon fluid molecules, but they are not falling so far in the Montreal Protocol. Then we have, of course, the impact of OH molecules, which have an ozone depletion through chemical reactions. Carbon monoxide has an impact on ozone depletion through chemical reactions. Then we have also iron particles, which are emitted by reentries, but also some of them are emitted during space launches. There's also some chemical reactions leading to ozone depletion. And then there are some surface effects for aluminum, which leads to a reactivation on inactive chlorine species. So this might also accelerate the ozone depletion here. And then we have, of course, the polar stratospheric clouds with surface reaction for nitrogen and chlorine species, and soot particles, which also have some surface reactions that can lead to ozone depletion, as it was, for example, shown for volcanic eruptions. And there might be also more species which we yet don't know that might have an impact. The ozone impact was also already measured. There was a fly through a plume done in the late 1990s by Ross et al. And they saw that there's a significant ozone loss locally, but this is also then after a few hours due to the around ozone is then closing the ozone loss here. It is therefore a temporary ozone reduction, and what is quite interesting that they measured the impact only during the day and not during night launches due to the missing photodissociation of chlorine molecules to chlorine atoms. Still, knowing all those effects, we estimate that the global impact is less than 1%, according to the last scientific assessment of ozone depletion of the WMO. And with that, I conclude my talk now with some take-home messages. So for the production phase, we know that this has a significant impact, but is limited regarding the insights that we currently have from science perspective. As mentioned, we are here really depending on data from industry, and lifecycle assessment and eco-design are required in the future to lower those impacts. For the launch emissions, we see that currently we estimate no significant global impact, but we might have a significant impact if we have other order of magnitude of launch rates. For the re-entry phase, this is currently a big research gap regarding the emissions that are there and also the impacts from those emissions. We know that the aluminum emission and also some other on the same order of magnitude as natural resources. And we also might have unknown species that might have a significant impact that we don't know at the moment. Therefore, we have to do a lot of more research in the future. But still, I want to conclude with a positive message because we still need space flight for research, communication, navigation, Earth observation. So we need to find a way to make spaceflight sustainable. Now, I would like to thank the German Space Agency for funding the research in the past few years. And there's also a follow-up project which was launched in 2025 at our institute, looking now at the chemistry of the upper atmospheric emissions. So the research gap that I mentioned. And with that, I would like to thank you for your attention. And now I'm happy to answer questions.
Thank you very much, Jan, for this very interesting talk. So now you are all invited to type in your question in the Q&A tab of this Zoom session. Meanwhile, maybe, Jan, I can ask you a few questions. One question I was wondering, how would you recommend legislators would use your results to legislate on maintaining the sustainability of space travel?
Well, it's an interesting question. I think from the knowledge that we currently have, we need to implement life cycle assessment as a mandatory step in the development of space transportation systems. For at least for Europe, this is underway under the PEF-CRs that I mentioned at the beginning, so product environmental footprint category rules. So this is then a need to do a life cycle assessment of your launch system when you develop it. But still, of course, we do have a lot of question marks regarding the launch emission and re-entry emission impact and the type of emissions that occur there. So also funding here from politics is required to further investigate on this topic. There's now a doctoral network coming up. It's called SLICE, so Space Launch Impact on Climate and Environment, which is led by the TU Dresden. They have now 15 PhD candidates in Europe and 3 in Switzerland, which will look at part of it, but we need more of those projects in the future. And also bring together different kind of expertise, because I have a background in aerospace engineering, but I have not really a clue on climate and ozone modeling. And of course, measuring also the emissions is not is a yet unknown way for me in the methodology. So we need workshops to bring all those experts together and then work together on this topic.
Thank you. And then just a practical, technical question. What were the main sources of uncertainties and how did you tackle them?
So for the launch emissions, we have a quite good knowledge about the propellant types that are used, and then we can estimate of course, with some uncertainties that I mentioned, the order of emissions. The impact of those emissions is yet very uncertain. As I mentioned, currently we only have factors for the troposphere and do not really know what happens in the stratosphere, mesosphere, and above. So this is really the big uncertainty that we have here. And on the other side, for the re-entry emissions, of course, the uncertainty which emissions occur. This also depends, of course, on which materials the upper stages are used for. Would say 95%. Normally, we know, for example, that there's an aluminum alloy or titanium and so on, but we do not know the exact composition of those materials, and there might be also some smaller amounts of maybe some other chemicals that lead to some emissions that might have a significant impact. So this is really yet a big uncertainty that we have.
Thank you. So there are some questions in the Q&A. I will read the first question. What are the major bottlenecks you would recommend atmospheric and climate scientists to focus on?
So the bottlenecks, I think, are currently the chemical reactions of the emissions and the knowledge of the emissions itself. So, to my understanding, what I've heard so far from climate scientists or atmospheric scientists is that they need to refine their models for those species that are now induced by the space activities. For example, on the different particle sizes, then how long they stay in the atmosphere, what are potential chemical reactions coming out from that. So this is really at the moment uncertain how to model all of them if we have, for example, emission inventory. To then model it completely, because normally the studies currently focus on aluminum and nitrous oxide, but there are also a bunch of other species which might have a significant impact. So maybe this would be a big step to build up here reaction chemistry database for all of those emissions.
Thank you. Another question I will read out. Will the Kessler syndrome have any long-term impact? Assuming there will be more small debris, can we assume that the material will be deposited higher in the atmosphere?
That's a good question. So currently, I can't really answer the question because I'm not sure what the exact impact of the size of the debris is regarding the emissions, because normally we only modeled upper stages so far. Maybe smaller fragments will easier be burned in the atmosphere than a big tank, which may also generate some lift. So it is hard to answer this question. It's a good question.
So I don't see any oh yeah, wait, I can see one new question has arrived. Is the unknown composition of the small number of military satellites an issue?
So if the unknown composition of regarding the materials, so for I assume that it's
Yeah.
regarding the materials. So I think military satellites are compared to the total number of satellites that we currently see, for example, from Starlink and so on, only have a small mass share, and also for the normal satellites, we do not really have a composition of the materials. We have some estimations, for example. Leonard Schulz published there a very nice paper about the impacts from that. but I think military satellites are only a small share of the total number of re-entering objects. So I think I would say in general, the unknown composition of satellites is definitely an issue, but it's not specifically about military satellites.
Thank you. Well, I don't see any further question in the Q&A. So, Jan, thank you very much for this very interesting talk. And so again, the talk and the previous talks are all recorded and available on the E-SWAN website and YouTube E-SWAN playlist. Thank you very much. Goodbye.
Thank you.